Let's talk about speed of light now and how we transfer those bytes. Good, we have at least 3 mathematicians in the room these days. I'm a mathematician as well. I didn't even think that I would ever go into engineering part. I wanted to be a mathematician for the whole of my life. So now I'm here. So networking. As you can imagine, we have a huge amount of data. And like you are sitting in the room, probably some of your data is like in the next room. As a result, like you can sync your files very, very fast. But we have like users not only here, we have users in California, in US. More like 50% of our users are in Europe and APAC. So 50% of traffic are generated not from North America, let's say. As a result, and what we want, technically, we want to offer the same sort of experience to every single user, no matter where they are, like in Europe, APAC, or US. Like people asking where our users are, like we have our data, but it's not a secret. Probably it's like GDP based. If you look into a GDP, this is where our users are. Like where the Facebook users are, probably our users are as well. So it's easy. So also we have all the like traffic levels per country, per ISP, per everything. So networking is like there are multiple parts of networking here at Dropbox, and evolution is also there. And there is also like going from AWS to native story as well in networking. So we used to use AWS services for many parts, even on the networking side, like back in the days. So data center networking, this is how we connect like machines within a cluster, machine within a rack within a cluster within a facility, like here, data center to data center. Data center to a points of presence to some telecom provider, and telecom provider like and last mile to the user. We present almost on every single sort of iteration here except last mile, but last mile for us is our desktop client. So you have a desktop client running. This is our edge. This is how close we can get to you and start optimizations in terms of networking, in terms of optimizing TCP stack, and make sure how we can deliver bytes to you as fast as possible. So once we completed, not when we completed, when we started a journey from moving our storage from AWS to our Dropbox, the Dropbox data centers.
Mitch, do you want to go to the next slide, by the way?
Oh,
yeah.
But that's fine. So what happened, okay, we figured out, okay, now we have a huge amount of data, how are we going to handle it? How are we going to transfer it? How are we going to put it on a wire and move bits left and right? And that was a challenge, I would say. So even transferring data between data centers was like a huge project for us. And you can imagine you can think, okay, now I'm user in Europe, or I'm user which is far away from our data center. Probably you can get me bytes as fast as speed of light, or based on the how long are the cables between me and your data center. Unfortunately, that's in 99% of the cases is not true, unless you invest in that infrastructure. So as soon as you can imagine, when traffic is going from client to Dropbox data center, it goes through multiple ISPs. Every single one can have a problem. Every single one can have a congestion. Every single one can black hole traffic. Every single one can do a lot of different stuff. So we can do, as a result, you can have a packet loss, and as a result, you're we're going to a nuts, but TCP window size can be very small. So the only option for us, if you want our users to experience a good performance, is to get as close to the user as possible. So we did it in a good way, as I mentioned. We at the beginning we started to build our presence within US, in EU and APAC, and we build it Amazon based. We base it on natively on EC2 instances, and figured out, okay, what we can do there. We build in-house a lot of software. We have our own L7 load balancer in-house. We have L4 load balancer in-house. We don't use any hardware load balancers at all. All of that is built in-house, running on commodity servers. So that was a requirement because we wanted to scale. We want to depend on any hardware providers because we want to scale from from X to 5X within a day if we want. And we want to be limited only by the number of servers we have, because we have a lot of servers. We have a free pool always. We can we can use those servers as a load balancers at any given point of time. So we built it on AWS at the very beginning just to sort of verify our theory. Is it going to help? As a result, we saw like 2-3x sort of performance improvement in upload, download files for users. And we saw, OK, it's not that sort of difficult because we did it multiple times in other companies already. The only challenge here, Dropbox is a very network-heavy company. Like, usually companies are heavy on like compute, storage, or network. Sometimes on those 2 out of 3. We are heavy on 3 of those. We are heavy on compute, on storage, and network. This is where the challenge is coming from. We are transferring like 2 terabits a second at any given point of time. And as a result, we tested, we validated our approach on Amazon and started to build our own. First one actually appeared in New York. It took us 6 months to build the first one. And it took us a year and a half to build everyone else. So I would say within 2 years, we built our edge. And now this is where we are. This is where we have our points of presence. So edge is a sort of a micro data center that we are putting in those cities. It's like we're going to collocations like Equinix and stuff, like putting like a couple of racks there, racks of servers, starting terminating TCP and TLS there, and we don't do cache. We don't cache anything there because for many reasons, for liability, for legal reasons, we can't cache any traffic on those ports. Those are simply proxies. It sounds simple, but it can give you a lot. So as soon as you're going closer to the user, you're eliminating like what I call a black internet. I mean, as closer you are, as lower the probability that there is like a bad ISP actor in the middle. So this is our approach. And going forward, we keep doing that because this is a successful story. Next year, we are going to expand in central US, Oslo, Stockholm, Berlin. And we'll keep doing even after that. So the advantage of that approach, once we are going local, there are a lot of challenges, but actually there are more benefits than challenges. Going local allows us to start working with the local telecom providers, building relationships there. As I mentioned before, Dropbox is very traffic-heavy sort of infrastructure. And there is a demand from our customers, from our enterprise customers, and from the telecom providers in those countries. They want us to build infrastructure there. So we are going for the users, but also we are solving some other problems at the same time. For example, telecom providers would love us to come. Actually, I forgot about Toronto as well. We're building one in Toronto this year. To come and start building relationships there because we're taking local traffic there. This is like a Dropbox door. This is, as you can imagine, for example, if you're buying like a Mercedes, you don't want to fly to Germany to buy a Mercedes. You want to go like somewhere here in Santa Clara, order Mercedes, they will deliver it to you, you are done. So this is where we are doing a handshake, like between user traffic and ourselves. And as close as we can do a handshake, as fast as we can deliver a file. So this is where we are today. And one of the big things what we are doing is peering. Dropbox is a heavy on peering. Half of our traffic comes to us via peering. So, and there is a demand on peering. Like many companies who are transaction heavy, technically no one wants to peer with them. All of us want to peer with us because there is a lot of traffic we exchange between like top telecom providers and us, big enterprises as us. We have an open peering policy. And yeah, peering is not only for saving money, no. The main reason for peering for us is reliability and performance, and controlling how we route users' traffic. And all of those points of presence, as you can imagine, there are many of them. It's not just not just a sort of software and tools problem. As you go from one to many, it's requiring us to invest a lot in like automation, in provisioning the POPs and stuff. Now, technically, if you want, we can land the POP within a day, and it's gonna work easily. So a lot of that is automated. So POPs can go offline, online at any given point of time. There is a lot of redundancy. We operate our own global backbone. Most of our backbone waves are already 100 gigs. So we want, going to closer to our user, we want to serve much better the local populations. We want to have faster connections, better security as we like intercept traffic much closer to the user, and we are like limited amount of bad actors in the middle. And network economics, this is another big part because we are starting building relationships with every single big telecom provider in those areas. And we are building our portfolio. As a result, we can always potentially get a better price since we have a variety of choices now. We don't depend on any single provider. And yeah, this is how we transfer bytes from data centers. Cool. James will continue.
Any questions about networking before we do networking stuff?
No?
Do you guys use from I mean, I'm sure you guys are big on load balancers and stuff like that. Do you guys use like the commercial tin vendors, or you use software defined? How do you guys approach it?
I mean, we use Nginx at some point. Everything else is like built in-house, but we don't use like a device-based load balancers, no.
There was a time period when we were ramping up where we used off-the-shelf load balancers because we just needed something. Mm-hmm. We didn't have the time to develop our own in-house load balancing, but Dzmitry's team since then is all homegrown load balancing internally.
Your internal, like within the data center, are you off-the-shelf switching, or do you have your own?
Within the data center, there are off-the-shelf switches, yes. So we're like, yeah. You will go to a data center.
Oh, yeah.
You can even identify who they are. So,
Yeah.
if you are smart enough, you can even see a distribution. So,
Sorry, did you say you actually use normal OEM switches?
I mean, we do use switches. Yes, we don't build switches ourselves. Okay. Yeah.
So the distinction is that load balancing versus actual switching. So any application level load balancing is all done in-house on commodity hardware, like literally compute servers. But switching, that layer is off the shelf.
Just OEM, okay.
Yeah.
Routers and switches, not yet.
Yeah.
Are you using any software-defined networking technology?
I mean, we do as since we are not doing like hardware load balancers. This is a step forward. We also like looking into, and actually we run in production a lot of like sort of, how to say in the right way, like non-modern switches as well. So like build on Linux as well. So we are thinking what to do with that. At this point, I think we're good where we are, but there is a room. Yes, we do SDN but not everywhere. No.
Is that like part of the architecture, or is that just sort of an extra thing that you're?
It's not a part of the architecture. Like switches and routers works fine. We have a good relationship with those teams, with those companies. It's more about like, are we ready for that? Like all of that is not free. When you're building it yourself, it means you're committed to managing it. You're committed to keep improving that. You're committed to too many things. And we are like in the space where we want to define what we want to do ourselves and what we want to offload to third parties. Like James mentioned before, we work with third parties where it makes sense for us, we think. We work with third parties where they are good. If they think they are good, why to build something else, unless it's like extremely expensive. But in ideal world, I'm in favor of SDN, but the manageability of that infrastructure is like probably another discussion for a couple of hours.
Yeah, network integration is a big topic at the networking field day event, obviously. And I'm curious. So, is the network just not that dynamic? I mean, you're adding systems, but you're not really changing things once it's up and running, right?
Our network is not that dynamic. No.
Yeah.
No. So, I mean, at any given point of time, we can predict how much traffic we are processing on the switch level, on the router level, in the POP. There is no the dynamic part is coming from failures. As soon as something is going down, for example, POP in Amsterdam goes down. As a result, all of those local users will be routed to a next closest POP, let's say, in Frankfurt or somewhere else. And this is where dynamic is coming from, and we are solving the dynamic problem like that with like over-provisioning sometimes.
So it's more on the WAN side that there's dynamism, not inside the data center.
Even inside the data center, things can go nuts. Switches are going down. I don't know, routers are going down. So it's more about how good we can like build our networking so we can survive those failures and stuff. So yeah.
There is some network awareness in the software layer as well, as I mentioned before, about how we don't saturate a new node. There's also intelligence around placement to avoid saturating, say, a cluster router between two facilities or between two clusters. So the software does have, it's not a clean abstraction boundary, right? The software does have some understanding of the topology and does know to route things on the storage side. Right? You can't have every developer at the company worrying about network topology. It's not going to scale. But something like storage, where you have just such large flows, you get some efficiencies out of actually.
We think that the networking is an infrastructure problem, not a software problem. We don't, as James mentioned, we don't our developers to think about network. Some of them have to think about network when you're developing like a product, new service. You should expect it just works, capacity is there, and redundancy is there, and we can survive a lot of failures.
So do you have like network level monitoring intelligence built in
Yeah.
throughout the stack? Pretty much like, for example, using App Dynamics to do?
Yep. Everything is inbuilt. We have eyes everywhere. We can even show you something. We will put down the rack. We'll show you our automation, how it's going to catch it, what's going to happen after that, and stuff. So we are very, very heavy on monitoring. Since if you don't monitor, you can assume that your system just broken. So a lot of data is coming, and since we have more data than people can analyze in that, as a result, we are analyzing the data automatically in many cases. So, yeah.
On the storage side, there's interesting, again, heuristics. Like, for example, a disk fails and the system notices pretty quickly. What do you do about it? Because you probably don't want to re-replicate the data instantly, because maybe the disk is going to come straight back up. Maybe the process crashed and it's restarting. Maybe there's a code push going on and the system is getting rebooted. So there's like different granularities of failures, and the system can recognize these. So if a disk is corrupt, replicate it straight away. If the disk just disappeared for a bit, wait some time period. If the machine disappeared for a bit, wait some time period. And we have actual intelligence in the software stack now that if a whole rack goes down simultaneously, it will check to see if the top of rack is healthy.
Yep.
And if it's a network problem, we'll give it some time. Obviously within our failure models, because typically it'll go off the network and come back up in 20 minutes. There's no use replicating data all over the place and causing turmoil because of that.
And just also to add to the failures, to what kind of failures we care about is for example, since we operate in our own private backbone, for example, if you speak about Australia, the networking infrastructure, one of the roles of the networking infrastructure to make sure Australian people can reach Dropbox, no matter what happened. As you can imagine, there are multiple paths from Australia to US. Some through Hong Kong, through Singapore, through Japan, there is one through Hawaii. And those are cables. And that region, every single month, someone will cut some cable. So as a result, we have a redundancy. If one path is down, we're going to switch to another one. So we partner with the big players there. So we have that redundancy, even to that level. When cable's going down, we are still alive. So,
do you have a complete network architectural topology or something, that obviously without all the low-level details, that you can share out that shows that different hops from client all the way to the back end?
Different hops from client all the way to the back end. Well, it's as many clients as you have, as many different sort of graphs you will have, I would say.
We do have a diagram of, say, the dark fiber that we use.
Oh, dark fiber, yeah.
That you can see?
Yeah, the dark fiber, all the backbone, all the edge infrastructure. Actually, the Dropbox tech blog is a very good resource where we are very open. There is everything about our backbone, everything about our edge, everything about our data center networking is in there. So we keep posting all of this stuff and sharing with the community. So, yeah.
So if you take a Dropbox client or an app running on the phone, does it connect directly through to your storage nodes running behind the scene, which are internet facing, or do they go through app servers on AWS?
No,
what does the architecture look like?
No AWS in the way, but the flow is, just say you're in Australia, your desktop client connects to a POP in Australia.
Oh, the POP.
Talking to a server.
Yeah.
That POP's just the proxy. There's no application sense or anything. That forwards you to a server, presumably in the United States, to what we call a block server, if it's serving blocks, which is the service that has the permissions to do encryption and all that compression and stuff, because that's pretty constrained to a certain set of services. That talks to the Magic Pocket front ends, which is like the abstraction boundary around Magic Pocket, and those then will go and route internally to the storage nodes, right, and which have the disk on them. So there's quite a few hops, but if one thing we might talk about later on, like Magic Pocket internally is about 3 to 5x faster than our experiences when we're using S3, for a variety of reasons, including more customized to our workload, and also we can co-locate our hardware, our serving closer to our storage. But the impact to the user is mostly the network, right? Because our internal is great, it's fast, right? S3 is pretty fast too, right? So it's the network optimization is what the user notices. So when they're seeing a 3x increase in speed, they're seeing that because they're actually going through an actual pre-warmed TCP connection via a POP that's over a sensible network path. It's not because of something going on in the back end.
And
Is it always going through the US? Everything you mentioned just now, you said it routed from Australia through the US.
The destination is US unless the user or company decided to store their data in Europe.
Okay. So only Europe is the exception.
Our primary storage is in the United States.
Okay.
There's certain cases where there's European storage, but primarily the data.
But the encryption, if the encryption kicks in, it's always through the US, or is that also in Europe when it's...
Encryption is everywhere. And every single path, there is no we don't transfer data unencrypted on a wire at all.
Okay.
And if you have European storage, there's no data at rest ever gets stored on an American server.
Okay.
That's the guarantee to the users.
And it's encrypted from the client side too. So I mean, basically nothing coming out of your computer is unencrypted.
Nope.
Back to the security. What about the traffic? So we analyzed the traffic north-south and the intra data center, and through the proxy to arrive to the final destination. But back to the data center, what about the security for east-west traffic? I mean, every pod or node transfer data. What about the security for that piece of this network segment?
It's like SSL between.
As I mentioned, as soon as the data is on a wire, it's encrypted. So
Okay.
no matter what, it doesn't matter if it's like in between data centers, in between POP and data center, in between user and POP and a data center, it's always encrypted. So
Okay.
data is always encrypted, yes. So there's no such a thing when we transfer user data unencrypted from data center to data center. Never.
But within the data center?
Well, within the data center, I would say if you have like a nodes like within a rack, even today we probably don't do that unless it's like some service, some old legacy one that is not even in a service path at all.
Yep.
So all user data is encrypted, no matter what.
Yeah, it gets messier in a data center, because it is a secure facility.
Yep.
But something like, for example, block content even though the communication is encrypted, the block itself was also encrypted. So for example, if you're replicating data in the storage system, that is encrypted data. It's not raw user content. Even though that is then going over SSL, so there's two levels of encryption, but the storage system itself just handles opaque content, which happens to have been pre-encrypted before it's been added.
And those other servers that you covered the sort of architecture of the storage nodes themselves. You mentioned a list of other hops, different servers like the proxy servers and everything else. So, for example, your SQL sharding that holds the metadata.
Yeah.
Where do they run?
Yes, so that's my current team. And they're all running. You'll see them today. They run the same facility.
But they don't run on the same hardware or the.
No, they're very different hardware classes. So there's like almost like a pop myth around like this model where you just have the same hardware class that every service runs on. That's just not how it.
Effectively, the app server stack. How do they look like?
They're running on more generic, what we call compute class hardware. So there's three major hardware classes. There are more hardware classes, but there's storage, compute, and database. Databases are pretty expensive, pretty high performance, SSD-based machines with a ton of RAM on them. And they're doing, our metadata system that we're currently working on does around 10 million queries per second. So that's a very high throughput service. And then there's the application stack is just generic. It's just compute boxes, right? They have disks in them. They have
VMs, bare metal.
What's the question, sorry?
VMs or bare metal?
Bare metal.
No, bare metal.